All right, everybody, welcome back. We are continuing our conversation about series. And last time we introduced what a series was and talked a little bit about how to accurately define what it means to add up infinitely many numbers in a series and whether or not a series converges or diverges. So today we are going to continue the conversation. We will describe what we mean when we talk about series being linear. So what does it mean when we talk about the linearity of series? We'll define a specific kind of series, the so-called geometric series. So we'll define what this means, and we'll identify whether a series is geometric. We'll calculate, if a series is geometric, we'll calculate whether it converges and what it converges to. And finally, we will end with a quick little test to see whether or not a series diverges. I should say, maybe to be more accurate, we will create a little test to determine definite sufficient condition to see if a series diverges. And we'll call this the test for divergence. Okay, so first of all, as a reminder, when we talk about series, we're talking about an infinite sum of numbers, which takes on this notation. So the sum as n goes from 1 to infinity of expressions of the form a sub n. So we will say that a series converges, or we did this last time, say that a series converges if its sequence of partial sums converge, right? So the partial sums, s sub n, was the first n elements of our series all added together, so a partial sum. And we could create a sequence of these partial sums, and we would say that the series converged to a limit L if and only if the sequence of partial sums converged to L, right? And this convergence was sequence convergence, which we discussed before the break. So one thing that we also discussed before the break was that sequences are linear, or they have this linear structure to them, that in the sense that you can add two sequences together to get a new sequence, and the new limit would just be the two original limits added together. Similarly, with multiplication of a sequence by a constant number or scalar number. And so what we'll see is that since sequences are linear, series are also linear. And what I mean by that is that the following bullet points hold true. Series have this linear structure. So if I have two series, a sub n and b sub n, and if my series a sub n converges to L, and my series b sub n converges to M, then I can conclude the following. I can add those two series together to get a new series, the series as n goes from 1 to infinity of a sub n plus b sub n. And that new series will converge to what we expect it to, right? It's a sum of two other series, and so it will converge to the sum of the two limits, L plus M. Similarly, if I have, if I have a series, a sub n, that is multiplied by a constant, this gives me this new series, sum as n goes from 1 to infinity, of c times a sub n, that will converge to just c times L. So with respect to addition between two different series and with respect to scalar multiplication, we have that series convergence is linear and it behaves as you might expect. And that would allow us to do computations like this, right? So suppose, or recall, the one and only series that we've actually seen to converge, and that's the series of 1 over 2 to the n. We saw that it converged to 1. Well, we can now compute objects like the sum as n goes from 1 to infinity of 5 over 2 to the n, or the sum as n goes from 1 to infinity of 2 over 2 to the n minus 1 over 3 times 2 to the n, right? And to sort of see these in action, it's sufficient to rewrite them. So this is a sum of 5 times 1 over 2 to the n, right? We, of course, remember that the summation and the 1 over 2 to the n, that converges to 1, right, as is sort of written up here. And so as a result, we get that this entire series converges to 5 times 1, or just to 5. Similarly, in this bottom problem, I can rewrite this as a sum as n goes from 1 to infinity of 2 times 1 over 2 to the n minus the sum as n goes from 1 to infinity of 1/3 times 1 over 2 to the n. Now you notice I'm not writing the sum as n goes from 1 to infinity. As long as we know that this is an infinite sum, an infinite series, I can omit that notation just to make this look a little cleaner. But what we have now is I've broken this up into its linear components. I have this constant times an expression that we know how to sum. I have this constant times an expression that we know how to sum. Each of those sums goes to 1, as we know, and so this entire thing just becomes 2 times 1 minus 1/3 times 1. So the whole thing can simplify down to 5/3. Okay, great. And so this is a little silly at the moment because we only have those, this one series that we know converges. But as we develop more series that we know converge, this linearity will allow us to examine different linear combinations of well-known series. All right, great. Okay, I want to talk about now a very specific kind of series, a so-called geometric series. And so a geometric series is a series where each subsequent term is calculated by multiplying the previous term by a constant number r. So let's take this first example, right? 4 plus 2 plus 1 plus dot, dot, dot. Notice, in order to get from one element to the next, I am multiplying by 1/2. And in fact, it's the same constant 1/2 for every single time or every single step that I make. So to get from one term to the next, I multiply by this constant 1/2. The same thing is true in these other sequences. Here, I'm going to be multiplying by the constant negative 1/3, right? And you can check to make sure that that's the same constant from every subsequent term. And here, I'm going to be multiplying by the constant 2. And so such a series is called a geometric series. And it turns out that a geometric series can be written in this really nice form, right? So a geometric series has this form that's written at the bottom. The sum as k goes from 0 to infinity of c times r to the k. So here, I just want to highlight a few things. The c is just going to be some constant. R is our positive constant that is the common ratio from one term to the next, right? So here r was 1/2, here r was negative 1/3, here r was 2. That's our r value. All right, so c is some constant. R is that ratio constant, and k is what we see down here that's being allowed to range from 0 to infinity. Now we use 0 this time instead of 1, which we've been using in the past. But I just want to highlight that if we use 0, that will mean that my very first term will just become a c times r to the 0, that's just c, plus c times r to the first, plus c times r to the second, plus c times r to the third, and so on and so on. Right, so that will be our geometric series will have this general form. And we can see now that our value c actually becomes the first element of our sequence. So here it was 2, here it was 5, here it was 4. And then r is this constant ratio that goes from one to the next. And so that's how we will interpret our geometric series. Okay, so that's what a geometric series looks like. If we know we have a geometric series, we might be interested in knowing whether or not that geometric series converges. And we can check this by looking to see what the partial sums, the S sub n's, look like. So we can calculate our series convergence by looking to see if our sequence of partial sums converges. And so here, let's take a look at a clever way we can do that. So what I have up here at the top is my sequence, or is my partial sum S sub n. And so that's going to be, notice S sub n is equal to c plus c times r plus c times r squared plus dot, 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 all the way up to c times r to the n. That's what our S sub n is. So I'm actually going to do something very clever to rewrite this. I'm going to do the following. I'm going to write r times S sub n. And when I write an r here, notice I'm just taking the same equation as above. I'm multiplying it by r. So I get CR plus C times R squared plus dot, 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 plus C times R to the n plus 1. Right, so I just multiplied every term by r. And now I'm going to take this line and subtract this line. Right, so I'm going to take one of my equations, subtract the other, draw a reasonably straight line here, straight as we can hope. And what we get now is S sub n minus r times S sub n. And let's see what happens. So I'm going to get this entire top row minus this bottom row. So we'll end up with a C, that's definitely there. But now notice I will get a plus C sub r, and then a little later I'll get a minus C sub r. So those will actually cancel. I'll get a plus C times r squared, and a little while later I'll get a minus C sub r squared. So those will cancel. Actually, every positive term up here will cancel with a negative term down here. These will cancel, positive, negative, until we're left with this final term, this largest term, which did not actually get a chance to cancel. So S sub n minus r times S sub n will actually equal C minus C times r to the n plus 1. Right? Do we see that? So in fact, by subtracting the second line from the top line, everything canceled out nicely except for this very first term up here and this term down here, which was negative. And so the very final thing I can do is I can take this first expression, I can factor out the S sub n, right? And so I get S sub n times 1 minus r equals C minus C times r to the n plus 1. And assuming, that's important, assuming that r does not equal 1, I can actually divide that down to the bottom over here. So we get C minus C times r to the n plus 1 divided by 1 minus r. And so we have this brand new formula for our expression S sub n. Now, what does that mean? That's great because now we can calculate whether or not our geometric sequence converges by taking whether or not our geometric series converges by taking a limit of these partial sums, taking a limit of this sequence, and we see that this will actually equal the limit as n goes to infinity of C minus C times r to the n plus 1 over 1 minus r. And notice, there's a lot of constants floating around here, but let's think about this. C is just some constant, that's not changing. R is just some constant, that's not changing. The only thing that is changing is this exponent on the r. And so we see, in fact, that only two possible things can take place, right? If r, let's say absolute value of r, is less than 1, and let's think about this. If absolute value of r is less than 1, then this term will get smaller and smaller and smaller until eventually this piece here will disappear and all that's left is a C divided by 1 minus r. However, if r is bigger than 1, right? So if our geometric series has a common ratio that's bigger than 1, that means that each subsequent term is getting bigger. That means that this particular piece right here is getting larger and larger and larger. And that means that this whole thing will diverge. And so now we have a nice formula to say what our geometric series converges to, assuming that the common ratio r is less than 1. Oh, clear all that. Okay. So I want to end this video with a very quick observation that we've just made, which is that if our series has individual terms that are getting bigger and bigger and bigger, the series itself must diverge. And in fact, they don't even have to get bigger and bigger and bigger. They simply have to be staying away from 0. So we have the following two facts, which are equivalent, and both are true. So if our sequence happens to converge, I'm so sorry, this should say if a series converges, let's fix that. Right, so if a series converges, then the terms in that series must converge to 0. So the individual terms themselves have to go to 0 if we can even hope to add them all up to get to a finite number. So if a series converges, then the terms of the series must converge to 0. Or equivalently, if the terms of a series do not converge to 0, we'll fix that one too. Or if the terms of a given series do not converge to 0, then that corresponding series must diverge. And this is called the test for divergence. It's a quick gut check to see if a series might just diverge if the individual terms do not go to 0. All right, that's all I got for this time. I will see you all next time.